Welcome back to COMP526. We'll look this time in our last unit at the range minimum query problem. It's a classic data structure problem that at first sight seems very innocent and easy, but is quite tricky if you look at it closely, and is used in many places to speed up things. And you've seen already one of those places. We'll come to that in a second. And so it closes off this last missing black box that we didn't look into at the time, but today we'll close that off, or today and next time. I want you to roughly know what this RMQ problem, so range minimum query, abbreviated, what that is, and how it connects to longest common extensions in strings, because that's the black box I referred to. We'll look at some simple solutions, and you will all be able to figure these out. And then we'll look at some combinatorial objects that are related to this in a somewhat magic way, if you want. If you first look at it, it looks really dubious, but then I think it's quite clean. And we'll see how we can use this plus another trick that you haven't seen so far to get the best possible solutions for this range minimum query problem. That's roughly the chapters that we'll look at. I'll introduce the problem, then we'll dive into some abbreviations and see the simple and then the fancy solution. So let's start with what this problem is all about. The range minimum query problem consists of being given an array, and these can just be numbers. So you're given this array ahead of time, and you can look at it and work your magic on it and take notes. And then at query time, you're given a contiguous range from I to j, and you're supposed to find the minimum in that range. And that's all. So it's quite fundamental. The array is static in this case, so we suppose the array does never change. That's why you can look at it in the first place, take your notes, and then the array remains the same throughout the time. Let's do a small example. And so here's an array of numbers. As always, we start counting at 0, indices start at 0, and the range is given as the leftmost and rightmost index that is included in the range. That's the convention here, which means that RMQ of 7 and 15, the minimum in this range, is any occurrences of the number 2. That's the smallest that occurs. And so what the RMQ function returns is the position. It's the index, not the number, not the minimum, but the value, not the value of the minimum, but the position where it is attained. And if there are several, we take the leftmost just to break ties in some way. This doesn't usually matter too much, but let's just pick one convention and stick with that. So we always want the leftmost position of a minimum in that range. Okay? Time to see if you are awake. So here's another small example. The question is open on Slido, but I'll leave up the array because I didn't copy that on the question. So here's an array and a sample query. What is the return value in this case? So we already have 14 votes. There's one or two people on the live stream now as well, so expecting maybe a few more 23. Anyone still busy in here? Then let's switch to Slido and show the results. I'll leave it open. So the biggest chunk is for 1, and that's the correct answer. And to do this, so we first pick out the range that is between 1 and 6. So you just look at this range. You can ignore the rest of the array. The smallest number in here seems to be 4, and it occurs as the leftmost position at position 1, the first here. And so 1 is the index that we return. Good. Now, what are we trying to do with this? And it all doesn't seem to be so well motivated or interesting, but I'll tie it to the application that you've already seen in a second. A few remarks before we do that. The whole problem is comparison-based. We just asked what is the smallest thing. So it doesn't really need to be numbers. It could be any objects that you can compare. And so we can just take numbers that are convenient to write, and they represent whatever object there really is. You've seen this over and over again with sorting. Unlike most of the problems we've looked at so far, there are really two running times that are interesting in this problem, and both are important. We first have the time that we spend pre-processing this array. You're given the array, you can look at it. And there's a second time when you query, when I give you some range, you should come back with the minimum. And that's a different type of running time. And we'll see that there's a certain trade-off between those two, indeed. Just for notation, we'll call a solution to write it this way. So angle brackets for two functions, 2 running times. Just the first is the pre-processing, and the second is the query time. Yeah, one more thing to note, because we're talking about a data structure. You're given the array, you build a data structure, you don't know which queries are coming. So I don't tell you up front, I will need this range and this range and this range. I just tell you, here's your array, and then afterwards, once you've built your data structure, there will be queries coming. So you don't know in advance which queries or which ranges are needed. And you can spend. It's kind of clear if you want to make use of this pre-processing step, you have to memorize something, you have to store something. And so you can use a certain amount of space for that. We will not look at this in much detail because the pre-processing time basically bounds the space as well. You cannot not really use more space than you have time to write something during pre-processing. And we'll see that in the cases here, the interesting space bounds directly follow from that. So the space is never more than the pre-processing time, and that's good enough for us. Otherwise, we would have a third dimension. You could also talk about reducing the space further. Good so far? Now let's see again. This is like in the last unit, I asked you about error correcting codes. What do you think is possible to achieve? Of course, without knowing much about this. So assuming you haven't looked at the slides already, there's no good reason for you to know this. But let's just see what you think is possible. So you're supposed to type an answer like this with 2 angle brackets and then 2 functions. Say, I don't want to prime you on anything, but put in any functions of n. Like n to the 10 and 2 to the n. I think these are ridiculously large that no one would really pick them. So your answer should really be two functions, okay? Something like angle bracket open, n to the 10th, comma, 2 to the n, angle bracket close. That's the format I'm after. Okay, some come through nicely, others are weirdly formatted. maybe you want to edit this. So there shouldn't be any p's and q's in your answer. It's just two functions of n, right? P and q is just the name of these functions. All right. So I guess the big answer is supposed to mean the first function is linear and the second is constant. And then we have n log n constant, linear, and log n, and billions of other combinations. Okay, I don't want to comment on this at this point. It's for you basically to make some guess and then see what comes out of it.